Hello, my name is Mohamed Nurbiyev and I'm a data scientist at the Institute of Smart Systems and Artificial Intelligence. Today we will cover decision trees. Decision tree learning is a non-parametric supervised learning method for classification and regression. Its main goal is to create a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. The decision tree has its root node, nodes, and leaf nodes, and is called decision tree because it literally looks like a tree. Decision tree inducers are algorithms that automatically construct a decision tree from a given dataset. Typically, the goal is to find the optimal decision tree by minimizing the generalization error. There are various top-down decision tree inducers such as ID3, C4.5, and CART. These algorithms are greedy by nature and construct a decision tree recursively. ID3 or iterative dichotomizer is the first implementation of decision trees. It builds the tree in top-down fashion. It's based on maximizing information gain and minimizing the entropy. It's a recursive algorithm and uses a greedy search. It selects the test using the information gain criterion and never explores the possibility of alternate choices. The next algorithm is CART, which stands for Classification and Regression Trees. It constructs binary trees, that is, each internal node has exactly two outgoing edges. The splits are selected using 2-in criterion. Post-complexity pruning is used. CART can handle both numeric and categorical variables. C4.5 is the improved version of ID3. Unlike ID3, it accepts both continuous and discrete features, and it can handle incomplete data points. The overall features of these three algorithms can be seen from this table. For further readings, you can refer to the links below. Let's try to understand decision trees conceptually. Suppose we have a following dataset of blue and red classes, and we want to find a decision that splits the dataset into two classes. Here we see that at x equal to 1.5, we can divide the dataset into two classes. And if we want to build a decision tree, our root node will contain the whole dataset. And if we split the data at x equal to 1.5 and take the part that is less than 1.5, we'll have the blue classes. And if we take the part that is greater than 1.5, we'll have the red classes. What if our dataset contained our third color? Our old decision rule wouldn't work. If we take x smaller than 1.5, we see that this side contains greens. Therefore, we should split further. Visually, we can see that y is equal to 3.5 is a good split. And if we want to build a decision tree, as in the previous case, root node will contain the whole dataset. And if we take x greater than 1.5, we'll have reds. And if we take the x smaller than 1.5, we'll have blues and greens. And if we split further and take y greater than 3.5, we'll have greens. And if we take y smaller than 3.5, we'll have blues. In the previous example, we assessed the quality of split visually. But the computers cannot do this in the same way humans do. They need a metric to quantify the goodness of a split. There are metrics such as Gini impurity and information gain for classification, and we can use mean squared error for regression decision trees. Before covering Gini impurity and information gain, let's cover the concept of information entropy. Information entropy can be used to describe the amount of unpredictability of a random variable. Information theory was developed by Claude Shannon, who was an American mathematician and electrical engineer. The entropy can be mathematically defined as the negative sum of probability xi multiplied by the logarithm of probability xi, where xi are the distinct events from the sample space. For instance, a fair coin has an entropy value of 1 bit because heads and tails are equally weighted and can be encoded by a single bit of information. Let's make the calculations for this example. A fair coin has the sample space of heads and tails. First, we calculate the probabilities of these events. Since the coin is fair, the probabilities will be 0.5 and 0.5 respectively. We can then calculate the information entropy as the negative sum of this multiplication between probabilities and the log of probabilities. And we know that logarithm of 0.5 is -1. After plugging in all the values, we calculate that entropy is equal to 1. A biased coin with 99% probability of heads and 1% probability of tails has an entropy value of 0.08 bits. Less randomness results in less information storage capacity. Let's confirm that this biased coin has the entropy value of 0.08 bits. We will calculate the entropy as in the previous example. We have probability of heads 0.99, probability of tails 0.01, and if we plug in the values, we will confirm that entropy is 0.08. How is this useful when constructing decision trees? Entropy is used to determine how much information is encoded in a decision. In next slides, we will see how this is used. For example, a dataset of only blues would have 0 entropy. A dataset of mixed blues and reds would have higher entropy. Let's calculate entropy for a simple case with 1 blue, 2 red, and 3 green. First, we calculate the probabilities. The probability of blue is 1 out of 6 and will be 1 over 6. And we calculate the probabilities for red and green the same way. And we get that probability of red is 2 over 6 and the probability of green is 3 out of 6. Furthermore, we calculate the entropy using the before mentioned formula. In our case, it will be negative sum of multiplication between probabilities and log of probabilities, specifically probabilities of blue, red, and green. And we already have that probability of blue is 1 over 6, probability of red is 2 over 6, and probability of green is 3 over 6. Plugging the probability values, we get that entropy is equal to 1.46. Let's consider this dataset, where we have 5 blues and 5 red. Before split, we have the entropy of 1. And if we split at x equal to 1.5, we will have entropy of 0 on the right side because it has only one color. And on the left, it will be 1 over 6 multiplied by logarithm of 1 over 6 plus 5 over 6 multiplied by logarithm of 5 over 6, which is equal to 0.65. Because we have 1 red and 5 blues on the left. Now that we have entropies for both branches, we can determine the quality of the split by weighting the entropy of each branch by how many elements it has. We have 4 elements on the right and 6 elements on the left, and we weight them by 0.4 and 0.6 respectively. So the entropy of the split will become 0.4 multiplied by 0 plus 0.6 multiplied by 0.65 and is equal to 0.39. We started with the entropy of 1 before split, and now it is down to 0.39. Information gain is how much entropy was removed. In our case, we removed 0.61. Gini impurity. Let's consider this dataset again. And suppose we randomly pick a data point in a dataset and randomly classify it according to the class distribution in the dataset. So what is the probability we classify the data point incorrectly? The answer to this question is Gini impurity. Now we randomly classify our data points according to the class distribution. Since we have 5 of each color, we classify it as blue 50% of the time and as green 50% of the time. So we have 4 events. Picking blue and classifying blue will have 0.25 probability. Picking blue and classifying it as a green is 0.25. Probability of picking green and classifying green is 0.25. And picking green and classifying green is 0.25. So we only classified incorrectly in 2 of the events. Thus, the probability is 0.25 plus 0.25, which is equal to 0.5. So the Gini impurity is 0.5. And we could calculate it by following formula. Consider a perfect split of 5 blues and 5 red, and let's calculate Gini impurity using this formula. G left will be probability of blue, which is 1, multiplied by 1 minus probability of blue plus 0, which is probability of red, multiplied by 1 minus 0, and is equal to 0. The same way we calculate Gini impurity of right side, which is also equal to 0. The perfect split turned a dataset with 0.5 impurity into 2 branches with 0 impurity. The Gini impurity of 0 is the best possible case. It is only possible if the split divides the classes into branches containing only the same class. So let's calculate Gini impurity for the imperfect split that we have. On the right side we have 4 reds and the Gini impurity will be 0. And on the left side we have 1 red and 5 blues. And the corresponding probabilities are 1 over 6 and 5 over 6. So the Gini impurity is 1 over 6 multiplied by 1 minus 1 over 6 plus 5 over 6 multiplied by 1 over minus 5 over 6 and is equal to 0.278. And how do we pick the best split? Before split, we had a Gini impurity of 0.5, and after the split, we have on the right branch Gini impurity is equal to 0, and on the left side, Gini impurity is 0.278. We determine the quality of split by weighting the impurity of each branch by how many elements it has. On the right side, we had the 4 elements, and on the left, we have 6 elements. So, we will weight the right side by 0.4, the left side by 0.6. So it becomes 0.4 multiplied by 0 plus 0.6 multiplied by 0.278, which is equal to 0.167. Thus, the amount of impurity we removed with this plate is 0.5 minus 0.176, which is equal to 0.33. We call it the Gini gain. Higher the Gini gain, the better split. For example, the Gini gain of the perfect split on our dataset is 0.5, which is higher than the 0.33. How do we train the decision trees? Let's use the dataset on the left with 3 classes. Our first task is to determine the root decision node in our tree. Intuitively, we want to the decision node that makes the best split. We will use the Gini impurity criterion to quantify the goodness of splits. For better understanding and simplicity, we will try every possible split. Note that it is not the fastest way to find the best split. For every feature, we will try all unique thresholds that produce different splits. Let's do an example in a gain calculation for the x is equal to 0.4 split. First, we calculate the Gini impurity of the whole dataset using the formula, and it will be equal to 3 multiplied by 1 over 3 multiplied by 2 over 3, where 1 over 3 is the probability of one class. We have 3 points out of 9, and it will be equal to 1 over 3, and 2 over 3 is 1 minus 1 over 3. And since it is the sum, we just can multiply it by 3 because we have same number of points for each class, and probabilities will be equal. Then we calculate the impurities for 2 branches. And on the left side, we will have Gini impurity of 0 because we have only one class. And on the right side, we will have 3.8, which is the probability of blue classes. 3 points out of 8 points multiplied by 5 over 8, which is 1 minus 3 over 8, plus 2 over 8, which is probability of green points. We have 2 points out of 8 multiplied by 6 over 8, plus 3 over 8, which is the probability of red classes, multiplied by 5 over 8. And as a result, we have 21 over 32. Finally, we calculate Gini gain by subtracting the weighted branch impurities from the original impurity. So our gain will be G initial minus 1 over 9 multiplied by G left and minus 8 over 9 multiplied G right, because we have one element on the left and 8 element on the right. Plugging in all the values, we get that our gain is equal to 0.083. We can calculate Gini gain for every possible split in the same way as before. And corresponding Gini gains for every split is listed in this table. If you look closer, we see that x is equal to has the highest Gini gain, so our root decision node used the feature x with a threshold of 2. In the previous slide, we found the root node. We calculated that at x equal to 2, we have the highest Gini gain. So our root decision node will use the x equal to 2. And our first part of decision tree will look like this. After constructing a root node, it is time to construct our second decision node. Let's arbitrarily choose the left branch. This time, we'll use only data points that would take the left branch, specifically 3 blues and 3 reds. To build our second decision rule, we just repeat the same process for every feature. If we try every possible split, we find that the best possible split is at y equal to 2. Our decision tree will look like this, with the second split at y is equal to 2. But when do we stop? Let's try to make a third decision node. This time we will use the right branch, and on the right branch we have 3 reds. If we try all the possible splits, they will be equally good, having a Gini gain of 0. Thus, we will make it a leaf node and label it as a red. So, if we are splitting and having a Gini gain of 0, we can stop. Pruning is a technique in machine learning that reduces the size of a decision trees by removing the sections of tree that provide little power to classify instances. Pruning reduces the complexity of the final classifier, hence improves the predictive accuracy by the reduction of overfitting. One of the techniques is called reduced error pruning. Reduced error pruning will consider each node for pruning and then make it a leaf and assign the most common class at that node. A node is removed if the resulting tree performs no worse than the original tree. Nodes are removed iteratively, choosing the node whose removal most increases the decision tree accuracy on the graph. Let's consider this decision tree consisting of many nodes. We split the data into training and validation set. In most cases, decision trees are prone to overfitting, so we will prune it to achieve better generalization. And we will test it on the validation set. As algorithm suggests, let's select one node. Let's choose this node. After choosing this node, we'll make it a leaf with the most common class. Let's suppose that this leaf is the most common class, and we will assign this class to this node and make it a leaf. After making this node a leaf, we'll evaluate the new tree on the validation set. If the resulting tree with the new leaf is not worse than the original tree, we print the node, meaning that we'll cut off the remaining nodes and leaves. Furthermore, we'll repeat these steps for each node until we cannot prune it anymore. Let's talk about advantages and disadvantages of decision trees. They are simple to understand and interpret. Use a white box model and work with numerical and categorical features. Require little data preprocessing. Non-parametric model, meaning that they don't require assumption about shape of the data, and they are fast for inference. But they are unstable, meaning that a small change in the data can lead to a large change in the structure of the optimal decision tree, and they are relatively inaccurate. But this can be remedied by replacing a single decision tree with a random forest of decision trees.